Hello friends, what's up? My name is Raghav and I have a very simple question for you. If you try to rotate a book about its axis over here, let's say I draw a book over here, and you try to rotate the book about this axis with some angular velocity omega, then you try to rotate the same book about this axis with the same angular velocity omega, and now you try rotating the book like this about this axis along an edge like this with the same angular velocity omega. Do you feel any kind of difference while rotating the book in case of all the three situations? Although the mass of the book has not changed, mind you, if the book was 5 kgs, in all the three cases, the mass of the book is 5 kgs. It has not changed. But what changes is the mass distribution. Mass distribution. And this very notion of mass distribution brings us to our topic of discussion for today's session titled Moment of Inertia. Now, moment of inertia is nothing but the rotational analog of mass. The rotational analog of mass. It's basically the property of an object to describe its stability. So it's a property of an object describing its stability and the forces that are required to change the motion of this object, along with the forces required to change the motion of an object. Now, you've all studied about translational motion, where you've heard this term inertia a million times, and inertia is nothing but the tendency of a body to remain in a state of rest or in a state of motion unless and until an external unbalanced force acts on the object, right? So similarly, when I talk about moment of inertia is nothing but the tendency of a rotating object to remain in a state of rest or in a state of motion unless and until an external unbalanced torque is acting on that rotating object, right? So it's nothing but the rotational analog of mass. We used to take inertia in case of translational motion as an equivalent of mass. Similarly, in the case of rotational motion, we take moment of inertia as a rotational analog or a rotational counterpart of mass. Moment of inertia is a scalar quantity. It's a scalar quantity. It's a scalar quantity. That means it depends only on magnitude and not on direction. Now let's have a look at the mathematical expression of moment of inertia. So moment of inertia, I'll write it as MOI, moment of inertia, can be written as integral of r square dm. Now let me just give you a simple example of this. Let's say I have a rigid body which is rotating about this axis, this dotted axis, and there is a small particle of mass dm over here, and the distance of this element dm is r. So if I am to find the moment of inertia for all these particles, small particles or small elements of mass dm, I have to take the help of integration and express the moment of inertia of a rigid body as r square dm. Also, if I talk about the mathematical form of moment of inertia, I can even mention it like this: summation of r I square mi, and I, let's say, starts from 0 to n, and this is basically moment of inertia for a system of particles. This is moment of inertia for a system of particles, and with the help of these mathematical expressions we can see that the SI unit of moment of inertia is kg, because dm mass, so kg into r square, which is the distance of this small element from the axis of rotation, and the square of the distance will give you meter square. So the SI unit of moment of inertia is kg meter square. I hope I'm clear till this step. Now we have an expression for the moment of inertia of a system of n particles, of n particles, right? But what about, you know, linear objects or objects which are distributed along a certain area, maybe 2D objects or 3D objects? These objects also will be having some kind of moment of inertia, yes or no? Like the way I just mentioned about the example of rotating a book about different axes, right? So in that case, the moment of inertia of the book in all the cases was different. Moment of inertia is basically characterized by the distribution of mass in a rigid body. Although the mass of that body remained unchanged, the mass of the book remained unchanged, but what was changing was the distribution of mass, and consequently the moment of inertia was changing for the book in every case, as we just discussed before. And that is the reason why a slight difference was felt when the book was rotated about all those axes. Okay, now let us have a look at a simple table. I will not be deriving the moment of inertia for these shapes. The reason being that the lecture becomes very long and it takes a lot of time. But if you're interested to learn the derivation of moment of inertia of these standard shapes, you can always connect with me on Google Meet. You can drop your doubts in the comment section, or you can just say share derivation in the comment section, and I will arrange a call on Google Meet with you, and we can have a discussion regarding the derivation of moment of inertia of various objects. Now, over here, you can see the moment of inertia of a solid sphere, which is 2 by 5 mr square, m being the mass of the sphere, and r being the distance from the axis of rotation. So, this axis of rotation, you can see over here, I'm trying to highlight my cursor also. So, this is the axis of rotation, and r becomes the distance from the axis of rotation. So for a solid sphere it is 2 by 5 mr square, and for a hollow sphere it's 2 by 3 mr square, right? So we'll be solving a couple of problems where we will be using these formulae, and over here you can see the moment of inertia similarly for all other shapes as well, about the center of mass, right, or about the geometric axis. So you can take a screenshot of it, so that whenever you solve any problem you have this handy with you. um, and if you want the derivation of the same, just post in the comment section, share derivation, and I will share a separate video, or I can schedule a Google Meet call with you where I'll share the derivation of all these objects with you, right? So that it's easier for you to get the mechanism of how the moment of inertia of any object, so of a solid sphere, is 2 by 5 mr square, or for a hollow sphere it's 2 by 3 mr square. You'll get to know the mechanism behind it. So if you want the derivation, you can just hit me up in the comment section. Now there are two very important theorems with respect to moment of inertia. So we'll be discussing about those theorems, and then we'll solve a couple of problems. So let's start off with the very first theorem, which is called the theorem of parallel axis. The theorem of parallel axis. Let's say I have a rigid body with me, and I'll try to draw a 3D diagram so that it's easier for you to visualize what I'm trying to say. Let's say this is my x-axis, and this is my y-axis, and this axis over here is my z-axis. Okay, I'll draw a rigid body over here. Please pardon my drawing, not very good at art, and especially on this computer. But I'll try my level best to make the understanding of this diagram very easy, and I'll try my level best. So yeah, this is my rigid body. Sorry. Um, Over here I have my origin, that is 0 comma 0, and let's say this is CZ. I'll name my origin as C, and let me take another axis named AB. Now I have a coordinate over here which will be 0 0 Z, and obviously why not, if I have a point in space which is named as x comma y comma z, let's name it as P over here, and P is labeled as x comma y comma z. So the z axis will not have any x and y coordinate. That's why I've labeled this point as 0 0 and z, and let me mark this point as Q. All right, now I will take a point over here. Let me name it as R. And again, one more thing that is known to us is the distance between these axes, which is D. Now if I am to find the coordinates of R, that will again be in this fashion, x comma y comma z. So x over here becomes D because the x coordinate till here is D. There's no y coordinate over here, so doesn't make any difference. I'll take it as 0, and over here I have z, right? This point over here is D 0 0, and now let me just try and join PQR. So I have joined PQ, I have joined PR. So yes, this is something that is ready now. And let me calculate the moment of inertia about this axis AB. Now, the importance of this theorem is that, let's say, if you know about the moment of inertia about the center of mass, let me just call it ICM, and the table that we just saw in the previous slide shows us moment of inertia of different objects about the center of mass, right? But if I am to calculate the moment of inertia about any other axis for a rigid body, right, which is not passing through the center of mass, then how do I calculate the moment of inertia becomes a question of great discussion. So let that moment of inertia about any other axis be I, which can be written as ICM, that is moment of inertia about the center of mass, plus mass of the rigid body, that's m, into d square, and d is the distance between the axis passing through the center of mass and the axis about which you want to calculate the moment of inertia. Alright, so in this case I am wanting to calculate the moment of inertia about AB, so let me just write AB over here. Now if I am to calculate moment of inertia about AB, that is IAB, right? I know that there's a point P over here which is at a distance of uh, x minus d whole square. We'll apply distance formula for these 3 points. So if I am to calculate the moment of inertia, it will be the summation, or rather not the summation, but mass of the rigid body, that's m, and PR square, yes or no? Obviously yes. And I'll try to simplify this a little. It'll be m, and I apply distance formula over here. So PR square will be nothing but x minus d whole square plus y minus 0 whole square plus z minus z whole square, and z minus z is 0. Let me just simplify this a little more, and this gives me m times x minus d whole square plus y square. Now I'll move to the next slide. I'll just write the same expression over here. So what we just got was m times x minus d whole square plus y square, and this was basically the moment of inertia about AB. This was moment of inertia about AB. And we'll simplify this a little more. So IAB is essentially giving me m x square plus d square minus 2 xd plus y square. So mx square, m y square, m d square, and 2mxd. Now if I use the principle of moments, then I know that m into x will be 0. M into x will be 0. So I am left with only m into x square, m into y square plus m into d square. This term has been neglected because of principle of moments. So that is the moment of inertia about the axis AB, along which I want to find the moment of inertia. Now we are supposed to prove that this IAB is equal to moment of inertia about the center of mass plus md square, and d being the distance between the axis passing through the center of mass and the axis through which you want to calculate your moment of inertia. Now let's try and calculate the moment of inertia about the center of mass. So now we need to know about ICZ. So ICZ is there with me, and that the distance of the point P has to be found from CZ. So I have to find PQ essentially, and again I'll use distance formula for the same. So this will be x minus 0 whole square plus y minus 0 whole square plus z minus z whole square. So that is my moment of inertia about PQ, or the center of mass of the body. So it's basically m times PQ square. Again I'll go back to the diagram, and m times pq square, because this is the distance from the axis passing through the center of mass. So again, if I use distance formula over here, I have x minus 0 whole square, y minus 0 whole square, and z minus z whole square, and I'll take an under root for distance. But since we have pq square, the under root will get removed and I'll be left with x square plus y square. So let me just write it down for you. So it will be mx minus 0 whole square plus y minus 0 whole square plus z minus z whole square, and since it's pq square, the under root sign will not be there, and you get mx square plus my square over here. Now notice one thing, this is mx square plus my square, which is the moment of inertia about the center of mass, and thus you have proven the parallel axis theorem. And this basically empowers you to calculate the moment of inertia of any rigid body about any axis passing through the rigid body, apart from the axis passing through the center of mass. Now let us move to the next theorem, which is the theorem of perpendicular axis, or perpendicular axis theorem. Now, we've seen moment of inertia for 2D objects and 3D objects. But this theorem, perpendicular axis theorem, is only applicable for plane bodies. So this theorem is only applicable for 2D objects or plane bodies. Okay? Not like the parallel axis theorem that was valid for 2D and 3D bodies. Okay, I have a rigid body. Let's draw a similar diagram. I have a rigid body over here, and this becomes my z axis, this is my x axis, and this over here is my y axis, and the origin obviously. Now let me select a point q over here, and let me select a point r over here. Okay, and let me select a random point p over here. So if I join this distance, let me make this line a little thick so that it's easier for you to identify. This theorem basically states that the moment of inertia about the z-axis is equal to the sum of moment of inertia about the x-axis and the y-axis. And let's try and prove this. Alright, moment of inertia about the z-axis, that is PO, right, over here, PO, and PO is basically equal to PQ plus OQ. PO square is basically equal to PQ square plus OQ square. So let's just do that. And by symmetry, uh, OQ and OR are the same. And we are supposed to find out these distances PR and PQ from the X and Y axis respectively. So, moment of inertia about the Z axis will be mass times PO square, because PO is the distance from the Z axis. So, mass times PO square, and this is equal to mass times PQ square plus OQ square. So, PQ square plus OQ square. Or I can write this as mass times PQ square plus PR square, because PR is the distance from the Y axis and PQ is the distance from the X axis. So I am left with moment of inertia about the Z axis, which is equal to moment of inertia, like sorry, mass into PO square is equal to mass into PQ square plus mass into PR square, and mass into PQ square is nothing but moment of inertia about the X axis, because this becomes X and this becomes Y. So Ix plus Iy. So Iz is equal to Ix plus Iy, and that is essentially uh, the proof for this theorem. Basically, PQ and PR are perpendiculars dropped from the point P on the x-axis and the y-axis respectively, and PO becomes the perpendicular to the z-axis. So basically, PO and the z-axis are forming this angle. So uh, I am basically applying Pythagoras theorem over here. PQ square plus OQ square is equal to PO square, and over here I can also write PR square plus PQ square as well, because if all these angles are 90, this angle also has to be 90, and I get mass into PQ square plus mass into PR square, and this is equal to Ix plus Iy, and the sum is equal to moment of inertia about the Z axis. So the proof of this is pretty simple, and you should remember that it is valid only and only for plane bodies. It is valid only and only for plane bodies. Now let's have a look at an interesting question. Although there are two ways to solve this question, I'll read the question out. The question says, find the moment of inertia of a uniform rod about an axis which is perpendicular to the rod and touches any one end of the rod. First thing, let's just draw the diagram and try to understand what the question is trying to say. So I have a rod over here. Let's say the length of the rod is L, the mass of the rod is M, mass M, and I am to find the moment of inertia about an axis which is perpendicular to the rod and touches any one end of the rod. So I take this axis, it's perpendicular and it's touching one end of the rod, right? And I am to find the moment of inertia about this axis, let's say AB. Alright, now let me solve this question using two techniques. Let's use the first technique of integration to solve this question. I'll select a small mass or a small element of width dx, And we know that moment of inertia is equal to r square dm. And if I talk about the mass per unit length of this rod, it will be m by l. So if for mass m the length was l, then for this small strip dl, what will be the mass? It will be dm. Let us calculate the value of dm. So I get m dx m dx is equal to l times dm, and I get dm as m by l dx. Now if I substitute this value of dm in this integral over here, what do I get? R square is basically the distance from the axis of rotation, which will be x for this case. So I get x square dm, and I know the value of dm as well. So it is m by l times dx, and I am to do this integration along the length of the rod. So if, let's say, if this point is 0, this point has to be l along the x-axis. If this is my xy plane, I start off with 0 and I have to integrate uh, till this length L, so I get 0 to L. Now I'll take m by L out because this is a constant, so we are left with x square dx, and if you integrate this for me, it will be m by L x cube by 3, and the limits vary from 0 to L, so I get ml cube by 3L, or I get ml square by 3. So this is the moment of inertia of this uniform rod about an axis which is perpendicular to this rod and touches any one end of the same rod. This I have done using integration. But we can also use the parallel axis theorem to solve the same question. Uh, I have this rod over here once again, and I will not be taking any help of integration. I'm using parallel axis theorem. Now this becomes AB, and if the length of this rod is L, mass of the rod is M, and if I talk about the center of mass, the moment of inertia about this axis, let's say CD, which is the center of mass, is something that we know. It is ml square by 12. And since this is the midpoint of the rod, this distance between the two axes over here will be L by 2. And if I use the parallel axis theorem, I am to find the moment of inertia about AB. So this is equal to moment of inertia about the center of mass plus md square. So this will be ml square by 12 plus I have md square. So d is L by 2, so this will be L square by 4. So I take LCM over here. So this is 4 times 3 equals to 12. 3 ml square plus ml square, that is 4 ml square by 12. And again I get the same answer, that is ml square by 3. That is ml square by 3. Let's have a look at another problem. I have 3 particles A, B, and C. All the particles have the same mass m. All the particles have the same mass m, and these particles are placed in such a fashion that the distance of point A from point B is equal to the distance between points B and C and A, thus forming an equilateral triangle. And let's say the length of this equilateral triangle, or the distance between these particles, is L. Okay, so let's find the moment of inertia about this point B. This is my axis about which I want to find the moment of inertia. Give it a thought and think about which theorem will you use to solve this question, and you can post your answers in the comment section as well, so that there is some engagement in this video. Okay, I'll tell you how to solve this question. Now, if you look at particle B is essentially lying on the axis AB, right? So the distance of particle B is 0 from the axis, and the total moment of inertia will be because of particles A, B, and C respectively. So moment of inertia due to B is equal to 0. So I'll be considering the moment of inertia because of particles A and C. Alright. Now, if I see the distance of particle C from the axis AB over here, uh, this is L. This distance is L. So if I calculate IC is equal to ml square. And if I am to calculate the distance of point A from the axis, see, this is an equilateral triangle. So if this angle is 60, this angle is also 60, and you know that this length is L, we can take the help of trigonometry. So I have 60 over here, and this is my right angle. So if this is, let's say, A, so I can say that cos 60 is equal to A by L, and A is equal to, cos 60 is half, so A is equal to L by 2. So the distance of particle A from the axis of rotation is L by 2. So this will be m L by 2 whole square. And this gives me I equal to m L by 2 whole square plus ml square, which is ml square plus ml square by 4. And if I add these two terms, I get 5 ml square by 4. No, now let us try and switch this question up a little bit. Let's not calculate the moment of inertia about point B. Instead, let us try and calculate the moment of inertia about any edge of this equilateral triangle. So let us try and calculate the moment of inertia about this axis PQ, which is on the edge of this equilateral triangle. Alright? So if I am to calculate the moment of inertia about the axis PQ, which is on the edge, you can see clearly that the distance of particles B and C is 0 from the axis because they are coinciding with the axis. So in this case, again, moment of inertia will only be due to particle A, and the distance of particle A from the axis PQ will be L. You have L over here, and this will be L minus 2. So if you apply Pythagoras theorem, or you can even take the help of trigonometry, so this distance over here, let's say B, this will be L sine 60. So the moment of inertia will be M L sine 60 whole square, and we know the value of sine 60, it's root 3 by 2. So I have root 3 by 2 square, and this becomes ml square and 3 by 4 over here, because root 3 square is 3 and 2 square is 4, and you get 3 ml square by 4 if the axis of rotation is about an edge of this system. So questions do tend to switch up a little bit in examinations and competitive examinations as well. So please be very careful when you are solving any kind of question like this. Now let us have a look at this question, and let this be the last question of this lecture, and we'll end the lecture over here after solving this question. It says, find the moment of inertia of a disk of mass 3 kgs and radius 50 centimeters about the following axis. First part, an axis passing through the center and perpendicular to the plane of the disk. So this axis is passing through the center and perpendicular to the plane of the disk. First, let's draw the system. See, drawing the figure really becomes very helpful in solving questions, because you get to know what the question is actually wanting from you. Right? Let's say this is the geometric center of the disk, and the the radius becomes r, and the length, the mass is m. All right, and we are supposed to find the moment of inertia about this axis, which is passing through the center and perpendicular to the plane of the disk. And for this we have a standard formula as well. For a disk, moment of inertia will be mr square by 2 if the axis is passing through the center and it is perpendicular to the plane of the disk. So let's substitute the values and see what we get over here. uh, in case the diameter, the axis coincides with the diameter, if the axis is about the diameter, or along the diameter, then the moment of inertia will be mr square by 4. So you can refer to the table that I just discussed a couple of minutes before, and you can take a screenshot of the same. So you have mr square by 2 over here, and the mass of this disk is 3 kgs. Radius is 50 centimeters. I can convert this to meter, which is half meter, and I have 2 over here. So this is 3 by 2 into 1 by 4. Okay, 50 centimeters. So all right. So this is 3 by 8, and if I do the calculation, I get 8 times 3 equal to 24. 8 into 7 is 56, and 8 into 5 is 40. So the moment of inertia in this case will be 0.375 kg meter square. So that's the first part. Pretty simple, and I hope there are no queries in this. Now, the question has changed a bit in part 2, and it says find the moment of inertia about an axis touching the edge and perpendicular to the plane of the disk. So now the axis is not passing through the geometric center, it is basically touching the edge and it is perpendicular to the plane of the disk. So the center of mass of the disk will be its geometric center, and we found out the moment of inertia in this case uh, in part 1. And now the new axis along which we are supposed to find the moment of inertia, let me name this as AB. So this is the distance between these two parallel axes. So if I am to find the moment of inertia about AB, it will be I cm plus md square, and I have all the values with me. D over here is the radius of the disk, and moment of inertia about the center of mass is something that I've calculated in the first part itself, and that is 0.375 kg meter square. So it will be 0.375 kg meter square plus md square. So d again is the distance, which is half a meter or 50 centimeters. So 375 plus another 3 by 8 we get over here. And I think so initially also we were getting 3 by 8. So 3 by 8 plus 3 by 8. So that becomes 6 by 8. Uh, I think so I made a mistake over here. Uh, about the center of mass, the value of moment of inertia, and that is mr square by 2, and d over here again is 50 centimeter or mr square. So this becomes 3 by 2 mr square. Apologies for the calculation mistake. I thought let's take it in terms of variables and then finally plug in all the values. So along the center of mass we all know that the moment of inertia is mr square by 2 for a disk, and we've already calculated the value of the same in part 1. And the distance between these two parallel axes are, so again mr square. So these two added together gives me 3 by 2 mr square. So m is 3 and r square again becomes 1 by 4, because r is half a meter, so r square becomes 1 by 4, and I have over here 9 by 8 kg meter square. Now let me do the math. 9 by 8, so this is 8, 1 so 8, and again 8, 1 is a 8, then 8, 2 is a 16. So it's approximately 1.125 kg meter square. This is the answer to part B. Now let us have a look at part C over here, and it says that now we are supposed to find the moment of inertia passing through the center and lying on the plane of the disk. So it's passing through the center, lying on the plane of the disk. Okay, so let's see the disk in 3 dimensions first. Let's say this is my z axis, this is my x axis, and this over here becomes my y axis. Okay, so we know the value of iz because this z axis is passing through the center of mass of the disk, and this will be mr square by 2. We are supposed to find out the moment of inertia about an axis passing through the center and lying on the plane of the disk. So this can either be Ix or it can be Iy. So let me just say Ix equal to Iy equal to I because of obvious reasons, symmetry, and Iz is equal to Ix plus Iy using perpendicular axis theorem, using perpendicular axis theorem. So Iz over here becomes mr square by 2, and this is I plus I. Although you can use the direct formula as well, but I prefer using the parallel axis theorem. So you get 2I is equal to mr square by 2, and I becomes mr square by 4. And you can plug in all the values and write down your answer in the comment section. I hope you enjoyed this video, and if you have any queries, you can always reach out to me on Instagram at the right angle with Raghav Raja. The link is in the description. Till then, take care, stay safe, and happy learning.